All right, welcome back. I hope you had a refreshing break. We have a very exciting afternoon ahead of us. So let's get right started with our next talk, Kubernetes Security Challenge or Chance by Marc Nimmerrichter from Certitude Consulting.
Thank you. Audio check? Hello, okay. So welcome to my talk. I will be talking about Kubernetes security. My name is Marc. I'm from Certitude. We are an IT security consulting company based in Vienna. Just a question at the beginning. Who of you has already played or worked with Docker containers? Okay, most of you. Who has already worked with Kubernetes? Okay, a few of you. Okay, I will have a short introduction about Docker and Kubernetes. I will try to keep it short, and then we will talk about the security aspects of it. So let's start from the beginning. Like a few years ago, we had monolithic architectures, which means that like an application was basically like one big thing, one deployment artifact running on a big application server or maybe a cluster, and all the applications, functions and features, they were all in this one WAR file, for example, if we are talking about Java. And yeah, that had the downside that whole development teams had to kind of coordinate their release cycles for their features to yeah, kind of have a new release of the whole big application. In the recent years, as we know, security development paradigms have shifted towards microservice architectures, which means that the application got chopped up into several parts. And each of these parts does just a small thing, like an account service just manages accounts, and an inventory service manages the inventory. And these components interact with each other, but they can be developed by different teams with different technologies, with different release cycles, even different development methodologies. So you just have to make sure that they have one API, a REST API most of the time, but yeah, they can work independently, and that allows like easier and faster deployment cycles, and yeah, independent technology stacks. So quick intro into Docker containers. So for those of you who haven't worked with Docker images, they are basically like an application's executable, but with everything, like all the configurations, all the file system, and everything the application needs in this one file. This has the advantage that the developer who knows the application can kind of prepare everything so that it can just be started and it should be running. Whereas previously, the developers gave their executables to the operations guys and they had to start it, but before they had to configure it, they had to install frameworks, libraries, and so on. Images are mutable, so once they are built, you can't change them. You can change them at runtime, but once you restart the container, it will be the image again, and your changes are lost. And images can be built on top of each other. So as we can see on the left side, that is an example from a Docker file. That's a configuration file that can be used to build Docker images. And we see, yeah, from the Ubuntu 21.10 base image, we built an image that installs iproot2 as a test file, defines the bash as the entry point, and that's basically it. And every command you see on the left from the Docker file results in one image layer that you see in the picture on the right. Above that, there is a read-write layer, and that's the only layer that you can write to, and it only exists at runtime. So you can write to the container at runtime, but once you stop the container, these changes are lost. Yeah, so that was images. Container is basically an image when it started. Technically, it's just a process, but it's a process that's a bit better isolated from other processes. And that's done by the kernel most of the time. And all the resources of the kernel are kind of abstracted away from the container. So the container can't see the host's network, the container can't see the host file system or the host processes, so it thinks it's the only application running on the machine. There is a container runtime. In Docker, it's runc technically, that sets up this process and configures all these namespaces and C groups and everything that's needed to have this isolation. So yeah, if we want to run a container, we just start the image. We don't have to set up a VM. We don't have to install any frameworks or libraries or dependencies. We don't have conflicts of like frameworks with other parts of the application. That's quite easy. And then a container starts up within seconds compared to a VM, which takes sometimes maybe a minute. So here's a picture that shows the difference between a virtual machine and a container. So the main difference is that the container, they share the same host, whereas a VM, they have different kernels. Yeah, sorry. So containers share the same kernel, and virtual machines have different, each virtual machine has their own kernel. That's important also for security. We will talk about that in a minute. Yeah, when we talk about Docker, we have to be aware that Docker is a term that's used for different meanings. So Docker can mean the whole like development approach. It can mean the company behind Docker. It can mean a Docker image. It can mean a Docker container. It can mean even the Docker client. So you have to be aware that yeah, what you're talking about. And Docker has helped to standardize most of their things. So now there are replacements, so Docker is not the only option. So you have other products that do a similar thing, but with maybe a few different approaches. So technically, we have Kubernetes that could start and manage my containers, or we could have a Docker CLI doing the same thing. At some point, they will start Containerd. Containerd will set up the network and set up the resources, and then over the OCI, which is the standard, it contacts the runtime, and the runtime will eventually set up the processes and the namespaces and cgroups and all the isolation mechanisms so that my process is a container. But as you can see, there are alternatives to Docker and Containerd. So Kubernetes also has CRI-O as an alternative. So since many things are standardized, you can kind of plug other things or other modules into this whole ecosystem. Yeah, and Kubernetes will remove the Docker shim in version 1.24. So that means, Docker as a runtime doesn't really play an important role anymore in Kubernetes infrastructures. That doesn't mean that Docker images and the whole Docker approach, it will still be there, but Docker as a runtime management will be removed. So what do we need Kubernetes for? In a microservice architecture, we have a lot of containers, we have a lot of services, we want to have redundancies, we want to scale up and down based on the load. So we need some product or some system to manage all these containers and all these dependencies. And that's what Kubernetes is for. So that's what a technical setup looks like. We have a master node, which has all the control plane. It consists of a database, which is an etcd. And the heart of it is the Kube API server. So there is a big API which kind of handles everything running in Kubernetes. There are some controller managers. They make sure that the right containers and the right number of containers are running and that everything works as configured. And the Kube scheduler schedules my workloads to nodes. On the right side, you see the nodes. It can be any number. It can be one or it can be a few hundred. They are controlled with the kubelet. The kubelet is the Kubernetes agent. And the kubelet makes sure that the node is part of the cluster and does what it should do. The kube proxy is a component that handles the networking. Kubernetes has its own overlay network, so to enable the communication between the pods, and that's what the kube proxy component does. Yeah, Kubernetes has a lot of configuration objects. You don't need to know all of them or understand all of them. The most important one is the pod. So a pod is basically the configuration in Kubernetes for one or more containers. And when you scale things up and down and when you manage your workloads, you're basically always managing pods. Even if there are multiple containers in these pods, the pod is the smallest entity you manage in Kubernetes. Then there are services which make your pods accessible from the cluster network. There are volumes to have persistence, because as we know, containers don't persist any data, so we need to mount some volumes to have persistence. And then there are some other configuration objects to scale and to make sure you have redundancies in case something breaks or a pod breaks, another one can take over. This is just a simple schematic example of services and pods and how they interact. So we can see here we have our containers. They are configured in a pod object in Kubernetes. We have a deployment, which allows us to handle releases. So when we want to upgrade to a new version, then we can do this with the deployment configuration. We have a service. The service makes sure that the pods are accessible through the network, because the pods could be scheduled on any nodes, and we don't necessarily know on which node the pod is currently running. So the service makes sure that the workload gets to the pod it's supposed to be. Replica sets, make sure we have redundancies and have multiple pods running at the same time. And we have volumes for storage. So that's just a simple overview of all these Kubernetes objects and terms. There are many more. This is an example configuration. On the left side, we see a Kubernetes pod specification. So it runs an Nginx in version 1.14.2 and on this port. On the right side, we have a service that references the Nginx app with this label. So and it makes it accessible on port 80 for actually the rest of the cluster. And everything is done in this declarative language. So Kubernetes makes sure that what's configured actually happens. And if I want to scale it up and down, then I just say, okay, I want to have 3 instances running, and Kubernetes will make sure that 3 instances on maybe 3 different nodes will be running. We have namespaces. Namespaces make it easier to work with multiple teams on multiple parts of the application, on multiple microservices, for example. So we have the kube system namespace, which holds all our control planes, so the kube API server, for example, or the kube dashboard, or the kube DNS, so all the control plane components. Then we have our actual workloads in other namespaces, so we can create any number of namespaces, for example, for our block. We have a team that works on the block, and they have privileges to access this namespace and configure all the objects here. And then there is another team that manages the web shop, and they have access to their objects. For everyone who hasn't seen Kubernetes in action before, we have I have a small demo here, which is a Kubernetes cluster. I just created a mini kube cluster from the web. And we can, for example, do a kube control, which is the Kubernetes client, and can say get nodes minus or wide for a bit more output, and then we will. Okay, maybe text size is too big for this. Let's do it like that. We see, okay, we have 1 node, and has been running for 28 minutes in this version. In the wider output above, we can also see its IP address and so on. We can also do a kube control get pods, all namespaces. So we see all the pod objects that are running, like the kube API server itself, the etcd database that we saw before, and all the other Kubernetes components. And if we want to start our own workloads, we can just create a kube control, run Alpine, for example, or we could also run an Ubuntu or whatever. We define the image, and we just sleep, and that's it. Now we can say kube control get pods in just our namespace, and we see that the Alpine image is running already. We can do a kube control exec it for interactive, so we execute into Alpine and we execute a shell, and now we get a shell in this container, and as we can see, we are root on this container image, and it has nothing to do with our host operating system. This is really the Kubernetes container. So kube control is the client that we use to interact with Kubernetes. Of course, theoretically, we could interact directly with the API, but that's difficult in practice, so we use kube control, and it will contact the API on our behalf. So let's talk about the security aspects of containers. So containers are just processes, and the kernel doesn't even know containers. The kernel only knows processes, and the kernel also knows namespaces and C groups. Namespaces are used for the isolation part of the process. So If a container or a process gets its own PID namespace, it means that it doesn't see any other process ID on the system. It thinks it's the only process running. If a container gets its own network namespace, it means that it has its own virtual network. And yeah, for example, if a local host application is running on the host, it won't be visible to the container. And for example, both the host and the container could have their web server running on port 80. That wouldn't be a problem because they both have their own virtual networks. So namespaces are kind of what hypervisors are in like virtual machines. So they make sure that containers don't see each other. C groups are for resource limits and resource restrictions. So they limit how many resources a process can consume. For example, how much CPU, how much memory, how much disk. And then we have capabilities, normal Linux capabilities that are restricted to make sure that the processes can't escape. Like there shouldn't be a capability sysadmin or systime to change the time, or sysmodule to load kernel modules. So all these capabilities should be restricted. There are normally seccomp filters that filter dangerous system calls, like the system call to adjust the clock, or a system call to delete modules or to reboot the system. So we want to make sure that these system calls can't be made from restricted containers. And then we have SE Linux or AppArmor as another layer of defense to restrict which parts of the file system the process can see and which system calls it can make. When I say these things, they always depend on the runtime. So most of these things apply to Docker, but they might not apply to another container runtime. So you have to be careful what runtime you are looking at, and their security levels might be very different. Especially, for example, Kubernetes disables the seccomp profiles altogether. So in Kubernetes, even if you're using Docker with Kubernetes, you don't have any seccomp filters. In newer versions of Kubernetes, you can enable this with a setting, but it's not enabled by default because they don't want to introduce any breaking changes. Yeah, and a container can run with a user, and basically, by default, for most runtimes, that's the same user that's also it's the same user on the container than it's on the host. You can use user namespaces. So they would kind of allow you to virtualize your users. Then you could be root in a container, and the host would know, okay, this root user is actually not root on the host system, but it's not enabled by default in most runtimes. So you have to enable it, that it might come with some complications. So generally, you shouldn't run a container or an image as the root user. You should try to avoid that. So what are container escape techniques? So the isolation depends on the runtime, as we have said. So it depends on which runtime you use, and it depends on which configuration of the runtime you use. And especially when you change the defaults, then be careful. Container runtime vulnerabilities exist, so you have to keep your runtime up to date, and especially also your kernel, since most of these isolation mechanisms are done by the kernel. You have to make sure that you are not affected by any kernel exploits. Yeah. We will see an example about a kernel exploit and how it can affect container security. So, for example, Dirty Cow it's already 5 years ago that Dirty Cow, this vulnerability was published. It's a vulnerability in the Linux kernel that handles copy on writes in memory. And it can be abused so that the race condition occurs, and that an attacker can use this race condition to write to memory areas that are actually shouldn't be writable. And there is an exploit for that that we can have a look at. It somehow works like that. We have different processes on the host. So we have the process A, which is running as root. We have another process B, it's not running as root. And we have a process C, which is actually a container. So it should be isolated. But all these processes share the VDSO memory mapping. So VDSO is an optimization from Linux to avoid context switches between the user land and the kernel. So some system calls are implemented in shared memory. For example, clock get time. Since many processes ask for the time all the time, we don't want to have a context switch. We just map this function into every process address space, so every process can just call this, this function and get the time. So the problem is, since this is a shared library, if this process exploits dirty cow to override this memory area, it will, of course, affect all the processes. And this is an example of a kernel exploit that can provide the container to escape by providing a reverse shell from a root process. Yeah, we can have a quick look at that. So, can you read that? Or yeah. So I prepared a Docker file to demonstrate this kernel exploit. So we built an image from the latest Ubuntu, and we add a compiler, and we add the exploit file, and we run this Docker image as a non-privileged user. We can do a Docker build. We give it the tag escape demo, and we build this image. And once it's built, let's first check we are running on Ubuntu as a non-privileged user. And when we run this Docker file, we'll just do a sleep again. Let's see if it's started. Yeah, we see this container with our escape demo image has already started. So we can exec into it with the bash. Okay, we see we are running as John on the image and not on the host. And we'll check my IP address. I will need that for the reverse shell. And where is it? Here it is. So these are the exploit files. I can compile them. And then when I start the exploit, I am root on the host and not in the container. So that just shows how simple it is to escape from a container with a kernel exploit, and how important it is to have up-to-date kernels. And we will talk about the security implications of that. So let's look at an attack chain. So how could we attack a Kubernetes or a container ecosystem? So generally, we have an app running in an image, or an app being deployed in an image. The image runs in a container. The container runs on the Kubernetes node, and the node is part of a cluster. So on the right, you see what an attack chain could look like. So once we get remote code execution in the app with some application vulnerability, we can get a shell maybe, only if the image is not hardened, because if the image is hardened, they might have removed the shell, but most people don't harden their images, which means you will find bash or whatever in the images. So the attacker can use that to then maybe exploit a kernel vulnerability and then be on the node. Then we can compromise the node, and from there we can, for example, find Kubernetes configuration files with secrets and then compromise the whole cluster. Of course, if we are already on the cluster, because it's a multi-tenant cluster, or we have already found some secrets to access the API directly, then we could go from there. So we don't need to bother with remote code execution in the app or getting a shell. Then we could directly start further down in the attack chain. Microsoft also released a threat matrix, that kind of summarizes some vulnerabilities in a Kubernetes or container ecosystem. So you can check it out. It's not complete, I think. So for me, runtime vulnerabilities and kernel vulnerabilities were missing in this matrix, but I think it's a good resource to just see or check if you have hardened your cluster and removed most of the threats. So what are common vulnerabilities that I've seen or that one can see in Kubernetes environments? What you often see is that pods are configured with higher privileges than they need. So you can, for example, create a privilege pod, and that basically removes all the capability restrictions and so on. You could also remove some of the namespaces with the host PID or host path flags. And some people do that for debugging or to get an application store data on the host. Actually, they should use volumes, but maybe because they don't know or whatever, they have their reasons to disable some of these namespaces. And as you can see, when all of these security measures are disabled, then it's an easy game. But this matrix just shows attack techniques when you see one of these weak configurations. For example, when we have the host path enabled, only the host path, then we could look for kubeconfig files on the host to give us access to the API server, or we could even get SSH access or get SSH authorized keys from the host file system and then connect to our host on SSH, or we could chroot into the host file system and so on. What's interesting is also if we have just a privileged flag and no other namespace is disabled, then there are also a few attack vectors. For some of them, there are Metasploit modules. For some of them, you don't even need them because it's just a one-liner to kind of exploit that and get access to the host. Yeah, so outdated software is probably one of the most severe vulnerability for container escapes. Also in Kubernetes, they have almost with every release, they fix some vulnerabilities. For example, there was an issue with symbolic links that allowed host file system access, or secrets exfiltration. So you could read other secrets from actually other namespaces that you shouldn't have access to. So keep your Kubernetes and keep your kernel and your runtime up to date. Another issue that I often see is role-based access control. So of course, you have your different namespaces and you can configure privileges for your users and your groups and define which user has access to which objects. But it's actually difficult because there are many objects and there are many users and there's a lot of room for mistakes. Regarding Kubernetes authentication, you should know that there is authentication, which identifies the user, obviously. Then there is authorization, which defines which CRUD operations a user can do in an object. So is a user allowed to create the pod? Is a user allowed to update the pod? Is a user allowed to delete the pod? And that, of course, also applies for all the other objects. And then we have admission control. Admission control is very important because it's the component that it's often overlooked. And if you only have authentication and authorization, it's easy to kind of bypass these restrictions, as we will see on one of the next slides. Yeah, we will see it here. So here we have a user that wants to access pod A. And the authorization blocks this user because, it says, this user doesn't have access to pod A. What the user can do, if the user has create pod privilege in another namespace, the user could create a privileged pod in another namespace and then use the host, because it's a privileged pod. It has access to the host. It can use the host to actually access the other pods. So the message is, there is role-based access control. It's very important. It restricts what the user can do on the API server. But don't forget that the workloads are actually running on nodes later on. And once you have kind of the ability to create pods, you can easily escape from these restrictions that are defined for the API server. What you can do to avoid that is to use admission controllers. Admission controllers actually look into the pod specification. So when you create the pods, you can use an admission controller to look into the definition of the pod. And then you see, oh, it's a privileged pod. I don't want a privileged pod on my cluster. And then you can deny that. So that will be one option to avoid these vulnerabilities. Or you could use different node pools. So you could give different users or different teams access to different nodes. Only, but that would be, of course, more resource waste maybe in some in some conditions. Yeah, Kubernetes is flexible. It's very modular. You can use many different modules. That's cool, but that also causes a lot of complexity. And yeah, every module needs to be configured securely. So you often find issues in the configuration of the different Kubernetes modules. The cluster might not be hardened. So as I said, seccomp is not enabled by default on in Kubernetes. So once you deploy a new cluster, that should be one of the first things to do, because to do it later on is difficult because you will be afraid to break things. You should use admission controllers, as I just explained, to really look into the workloads, and even if a user has create pod privileges, for example, to just make sure that the user can't create privileged pods to escape containers. Often you find debugging artifacts and like configuration that was intended for testing, like anonymous authentication, for example, that basically disables authentication. And yeah, you often find these configurations in production clusters. And also secrets in images, that's also a topic. So even Microsoft had an issue that I reported beginning of the year. They hard-coded their DP API encryption keys in the image. So not only is it publicly available to everyone, it's even the same for everyone. So I could just decrypt anybody's DP API encrypted blobs by just running my own Microsoft container and just decrypting it. They completely forgot about DP API apparently when they implemented their Docker images. There are some issues even outside the cluster. So in most cloud environments, so if you're running your Kubernetes in the cloud, then you might have a metadata service, which kind of can be abused to get information about the cloud context and the cloud environment. And also like other vulnerable applications might be running on the network outside the cluster. So that's also an attack vector that needs to be considered. Important also when you think about firewalling, so if you have already your corporate infrastructure and you have your existing firewalls, then be aware that by default the cluster shares like one IP or shares a set of IPs, and it's difficult for the firewall here to differentiate between the different services. So services that you want to firewall from each other, you either need to put them into different clusters, or you need to make sure that you have a different IP address per service somehow. That can be configured. It's a bit more difficult. So just when you design your cluster architecture, be aware of that. Yeah, I wanted to have a short discussion on multi-tenancy because some of my clients, they want to use big clusters for many teams and even for customers. And they're not really aware that by design or by default, Kubernetes is not secure for multi-tenancies. So even if you have different namespaces, it's very easy to like bypass these restrictions. How do cloud providers do multi-tenant clusters? And actually, they don't. So in Google, in Amazon, in Microsoft, their Kubernetes offerings usually give you a separate virtualized infrastructure. So they give you separate virtual machines and for your cluster. So they rely on the hypervisor virtualization. What about their container as a service offerings? Basically what they do is they either rely on virtualization again, or they have some like secure runtimes. And that brings me to my next topic. So Docker is just one runtime, so technically it's runc, and it uses the host's namespaces and C groups and so on to isolate a process. But there are other approaches, for example, one by Nabla containers. That's a container runtime that can be used, which basically implements most of the kernel in the user space. So it has a library operating system, and I think it only needs 7 or 8 system calls instead of 200 or 300, and implements like all the networking and everything in user space. So if something breaks, it will break in the process, but not on the host kernel. Another approach that is used by Amazon for their container as a service offerings is what they implement in Firecracker, or Kata Container is another independent implementation of a similar approach. They use lightweight VMs. So they use a hypervisor and they have microkernels running for each customer at least, or even for each container. Basically, they all implement the Open Container Initiative specification, which means that you can use these runtimes like a normal Docker container. So it behaves like a Docker container, but actually, technically, it's a VM. And then Google, in Google Cloud, you can activate gvisor, which is another container runtime that's similar to Nubler. So it implements most of the operating system in user space, in the gvisor process. So yeah, again, if something breaks, it will break in user space and not in the kernel. And it also kind of interprets all system calls. So it doesn't just pass them on to the host kernel, but it will kind of check them and perform some sanitation. So this is how the cloud providers provide their multi-tenant services. And of course, the container runtime is only one part of it. You need to have really a secure architecture, also considering network separation, access control, and all these sort of things to have one of such multi-tenant clusters. Yeah, not all is bad. So from my opinion, Kubernetes also has a lot of advantages, and containerization has lots of advantages. I mean, first of all, you have a lot of tools, even free tools, that you can use to identify these configuration issues and vulnerabilities that I have just talked about. There's a lot of free and open source tools. There are some commercial tools. So that's really positive. And on the other hand, you can do things that you couldn't do in a monolithic architecture. So you can harden your images. You can remove the shell, the package manager. You could remove all networking tools like curl, wget, or even IP and diffconfig. You don't need all that in the container. So you can really harden the container, the image file system, so that even if an attacker gets remote code execution in one of the containers, it's very difficult for the attacker to exploit that. Another advantage is that we have a lot of small services that can be that are easier to understand for a security guy or for a developer. So we can create security profiles. We can really restrict the processes that are allowed to run. We can restrict the network ports and the connections that can be made. So we can easily, with network policies in Kubernetes, for example, we can use network policies to really restrict what each service can do on the network. So yeah, we have granular containerization, and if something breaks in one part, it might not affect my whole architecture or my whole infrastructure. It just affects one little part of it. Yeah, so actually that's it. If I haven't exceeded my time limit, then I can answer some questions. Thanks for your attention.
All right, thank you very much. Are there any questions from the audience?
Over there.
Yeah, thanks you for a talk, very interesting. One question from my side, what I often see in container environments is that customers forget to update and keep their containers securely. For example, they create containers or bots with some Stone Age Ubuntu because their application is just working with this version, and then they kind of forget, yeah, I need to upgrade this. And of course, you can do a scanning and tell them it's too old, but they often don't have the mechanism to upgrade thousands of containers, or maybe just a few hundreds. But is there some tooling you can recommend, or some way how to help them? This is something I usually don't have a good answer, except of telling them keep updating.
I mean, yeah. So what you could do is you could use the latest tag, the latest image tag, and make sure that you pull the fresh version of the image every time. So there's a configuration in Kubernetes and also in Docker to not use the cached images, but to pull them. And yeah, when you use the latest tag, you always get the latest image. But of course, that could break your application if an update introduces a breaking change. So that might be difficult. But yeah, for a non-critical application, you could do that. Of course, as you said, you can use scanners, image scanners, but for larger environments, what I see that you are just overwhelmed with all the vulnerabilities because default Ubuntu or Red Hat, even if it's the newest version, you will find, yeah, probably like 100 vulnerabilities. And that's difficult to handle, so you can't really, because most of them won't affect you, so you can't manually analyze all of them. So what I recommend my clients is to just regularly pull the newest base image versions. What you could do is, as a development team, not wait for your next release to update the image, and even if the application or the microservice is finished and is not under active development, you should still automate your CI/CD pipeline to just make a build, even if you don't introduce an application change, just to get the latest base image version. So you could use the CI/CD pipeline to just regularly rebuild the images. But yeah, it's not easy. Yeah? So this part, like updating, is not automatically resolved.
Thank you. Are there any other questions? If not, oh, you have a question, sorry.
Maybe just one question in terms of the tooling. You were listing already Kubebench and all the others. So the first question is just how much is actually for you then manual work and how much do you rely on the tooling, because the rest would actually be with kubectl, right?
So when I do an audit, you mean how much I rely on tools and how much I do manually? Yeah, I mean, it's mostly, I mean that the tools just, where is it? It's here. The tools help me, for example, to check role-based access control, because you have many objects, you know, it's just a lot of data, and these tools help to have kind of get a matrix or something that you can that's easier to analyze. Yeah, so I use the tools just to check if I missed something, and it also depends on how big the environment is and how much time I have available. If I have enough time, I do my checks manually, and then I just confirm that I didn't miss anything with the tools. If I have like an audit for a large environments in just a short time frame, then of course I use more of the tooling to just be more efficient, and I might miss something that I would be able to see manually, but yeah, that's just the way it is in a time-boxed approach. Yeah.
Okay. And one more thing, do you think that in the next 2 years these tools might simply vanish? Because a lot of, in AWS, GCP, there's of course a lot of security monitoring and logging happening, and it seems you already get a security scoring, and if you have an AWS EKS cluster, then they can do this, of course, already within the environment.
Exactly, and the cloud environments, you have your security monitoring and your kind of security baselines, and it will, it might show you like many of the things the tools show you as well, so you're right, but that only applies to cloud environments, and I still have some or many customers that have like on-premise, especially large organizations, still many of them rely on on-premise setups. Right. There are also commercial tools which kind of are similar to what cloud providers offer as well, that kind of do things that many open source tools do, but they just put it all together in one dashboard and make it easier to process and to integrate into workflows in your organization.
Okay, thank you.
Thank you. More questions? Oh, there is a question from the stream. Okay.
So Falco Weiss asks, what are the 3 most important steps to take?
3 most important steps to take to secure a Kubernetes cluster. If I have to name 3, it's probably keep everything up to date, all your components. Don't change too much of the default configuration except to like harden things and improve things. And have a secure design and architecture, and it really depends on your use case. So if you are like multi-tenant, you have to consider all these issues that I just explained, or you just go for separate cluster for different teams, and then you can avoid all these multi-tenancy issues.
Thank you. Oh, one more question, okay.
I've just seen in your list here that you're also referring to Kubernetes crew plugins. Do you actually install plugins also in production environments like this? Because they would basically be coming from not really trusted resources in that regard, right?
No, a crew plugin, for example, that's a plugin for my kube control Kubernetes client, so it runs on my testing machine, so it wouldn't be installed on a production Kubernetes.
Okay, gotcha.
All right.
Yeah, but of course, as with open source tools, always, check them out. Like no warranty for any of them, and do your own research.
All right, one last question.
Hi, do you think it's viable to use containers to isolate malicious code? So would you be able to set up a container in a way that you could give somebody a shell account in it, and you will be fine? You won't be able to exploit.
So you mean to analyze malware or things like that in a container?
Yeah.
So I wouldn't recommend that for all the issues I just explained. Yeah. So I would rely on something, or you have a container runtime that, you could do that with some of these approaches like Firecracker or something like that, that really give you something that behaves like a container, that you can use like a container, and that's even fast, not as fast as a normal container, but faster than a traditional VM. But you have the hypervisor and you have a separate kernel. That would be more of a security boundary, but I wouldn't use the normal Linux kernel containers like the Docker or runc for these things.
Okay, thank you. Yeah, that's something I saw earlier, years ago, when this container thing came, that people use that instead of virtual machines in order to isolate. And I always said to people, so this is not isolation, it's not security here. It's more safety, right? So I wonder if this have changed, right? I'm not super up to date there.
Yeah. So you will always have a big risk, and not even the big cloud providers, they don't rely on container isolation for security. And so even if you do everything right, there might always be a kernel 0 day or something. So I would never use it to analyze random malware.
Okay, thank you.
Thank you. All right, if there are any more questions, you're going to have to continue afterwards. We're a bit short on time, so many questions. Okay, thank you very much.
Thank you.